Now, let's look at the picture here. I know it's in black and white, but you can kind of see what's going on, right? And the cool thing about this picture is you can actually see all the level curves associated with this. Okay, so for example, if I just trace this out, some of these, I have this level curve here. I have this level curve. And I have more in between. Now, speaking of minimums and maximums, right, as you could tell through the picture and each individual level curves themselves we have, right, there are places where there's local minimums and local maximums, right? So like here could be local minimum maximum because it curves up, comes down. This could, local min because it doesn't go anywhere. Same thing here, 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 right? Anywhere there's a little divot, there's mins and maxes. And just like single variable calculus, we also have absolute mins and absolute maxes themselves. Okay, and that's what we're going to be dealing with in this section is how do we find the minimum and maximum values of a level curve or throughout the curve or the surface itself, given different types of level curves. Okay. So before that, let's define how to find a critical point, just like it was in single variable calculus. So given two function, two variables, it has a local maximum, just using the same general definition as single variable calculus. If f of xy is less than f of ab, or x and y is nearby ab, then the number is called a local maximum, right? So basically, this is happening, right? This one has a local minimum at a and b if everything is now greater than it. So just like normally, right? Everything's smaller than it, everything's bigger than it near A. And then F has a local min or local max at A and B, and the first order partial derivative of X exists, then we have that. That's an interesting part. Now, this is how we're going to find our something called our critical points, just like it was in single variable way back in the day, right? So we're going to set them both equal to 0, and those points that equal 0, the derivative equals 0, are called our critical points themselves. All right, so let's try this out. So find the critical points of all extreme values of the function here. Okay. So let's first find both partials, and we'll set them equal to 0. So take the derivative with respect to x only. Yeah, that's it. And respect to y, since we're here anyways. There we go. Okay. So now the next step is just to set it equal to 0 and just solve. So solving for x, we get x equals 1. Solving for y, we get y equals 3. So we have one critical point. 1, 3. Okay. So now we're going to plug in 1, 3 into our function and see what we get out. So plug it in everywhere, and you should get 4 out. Okay. And now all we're going to do is check, is it a local minimum or a local maximum? Okay. So to do so, it's a little weird concept to do so. We'll get to much more detail, like straightforward, like the second derivative test gives you this and that. But thinking just arbitrarily how this is going to work out is we're going to plug in negative x and negative y and see where that goes. So if I plug in negative x and a negative y, into here. We know that's going to be greater than or equal to 4, right? The value we're looking at. Now, if I plug in any arbitrary x and y that's, bigger than 1 and 3, that's also going to be greater than 4. And if I put any other combination we want. So now if y is negative or if x is negative, these are also going to be greater or equal to 4. And then these are arbitrary values. That's a key thing. So because these are always greater than 4, this is considered a minimum value. Now, again, this is more theoretical when it comes to it. You plug in any arbitrary x and y you want. But again, don't worry, we'll actually get to a theoretical, actual definition to do so. But, this is the only definition we have so far. So we just pick any arbitrary x and y to satisfy these conditions. Okay, so now let's actually get to an actual, what do we do when it comes to it? So, one more example. Find the extreme values of our function. So take a derivative, set equals 0. Oh, so we get the point 0, 0. Okay, so now if I plug it into our function, well, we get 0. So the question is this a min-max itself? Okay. So if I plug in 0 in for x and plug in any arbitrary y value I want, what's happening? So this goes away, right? Any arbitrary y value, like 500, it's going to be negative. So this is going to be less than 0. If I do it the other way, and I plug in any arbitrary value for x and set y equals 0, that's going to be greater than 0. So they kind of contradict each other, right? So because they contradict each other, this actually is not a critical point. So this has no critical values. Now, if you guys remember way back in the day, if they were not considered a critical value, therefore they were considered something else. And these are called saddle points. So this point right here in our question is considered a saddle point. Okay. Now, what in the world is a saddle point? Now, in 3 dimensions, it's much easier to understand what a saddle point is than in 2 dimensions, because kind of stole these pictures from the internet, but think of a saddle point kind of like the ridge of a Grand Canyon or a canyon, okay, where from here to here is looking like this, and from here to here is looking like that. So depending on the point you're at, let's say here, either you're at the top of your trip or at the bottom of your trip. Because if you go down this way, you're going down. But if you go up this way, you're going up, meaning it's the smallest value of your trip or the highest value, depending on what you want. Now, an easy way to look at this is, hopefully I could draw this out for you guys, something like this. So I walk this way up my hill. So at this point, yep, and I'm going to go back down on the other side. So according to my trip, this is the highest point, and I'm going back down. So this is a maximum value. However, if I started here and did my trip, and go all the way back up here. Therefore, this point here would be considered a minimum point throughout my curve. That's what saddle point represents. Depending on the direction you're going in, it can either be a minimum value or a maximum value, or a low point or high point, right? Depending on what you actually are doing. Okay. So that is what a saddle point actually represents in 3 dimensions. Now, before we get anything further, let's do actual definition instead of doing this, weird stuff and plugging in stuff. We get our second derivative test. And the second derivative test is much easier than the single variable calculus because it only has to check one thing instead of checking both things. So this one says, suppose the second partial derivative of f is continuous on a disk with center A and B. And suppose the partial derivative f and y equals 0, right? We can actually find critical values. Therefore, this is considered our second derivative, or our directional derivative. Okay. We'll call that D. So it's the second partials multiplied together minus its mixture squared. Okay. And again, it's all at the point, so we're going to get a value out. Okay. Now, this is the nice thing about the second derivative, is all it cares about is this part. Because if this number at the point A and B is greater than 0, then we may have a local minimum. If this part is less than 0, we may have a local maximum. However, if this value is less than 0 and this is not true, then it's considered a saddle point. So nice, straightforward, just check, 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 which is pretty nice. And then remember, notice we just have to find second derivative, which we find it anyways. So we just got to check 2 numbers. Does it satisfy which case in that scenario, which is much easier to deal with itself. Okay, so in that case, like everything else, let's try some examples out. And give me 1 sec, because I may have accidentally not given that one out. Oh yeah, I thought I messed up. All right, real quick, this is supposed to be greater than. That didn't make sense. There we go. So just quickly change that to be greater than. I was wondering why didn't that definition really make sense. So the D value has to be greater than 0. If it's less than 0, it's automatically a saddle point. There we go. I remember that'd be much easier to understand. So let's try an example out so you can see how this is going to work. So find the local extreme values and the saddle points, if we have any saddle points, of our function here. Okay. So we have a lot to do here. So first, find the partial derivative with respect to x and y. So 4x to the third minus 4y. Take derivative with respect to y, 4x to the third, or 4y to the third, minus 4x. Okay, so now we set them equal to 0. And now we solve. This is interesting, right? So we can factor out a 4, get rid of it, and we'll have this. So therefore, we have that happening. Well, that isn't good. Maybe we'll have more luck on the other side. So if we factor out a 4, well, that also goes away. And we have that. Okay, oh boy. What do we do now? Well, we could just plug this in and see what we get. So instead of y, we'll plug in y to the third. So just straight out substitution. So we get y to the 9th equals that. which breaks down to be, if you factor out an x, gives us this. And if you guys remember your difference of squares formula, this factors even nicely, even breaking down. And this breaks down even more. Again, due to difference of squares. And again, we can factor it one more time. Oh boy. But don't worry, we live in the real world, so these will never be zero. So in fact, all we care about is these parts. There we go. So therefore, if x is 0, 1, and -1, we can go back here. So we have 3 critical points, or potential critical points, right? So if x is 0, y must be 0. If x is 1, y is 1. And if x is -1, well, -1 to the third power still gives you -1. So there we go. Those are 3 points we could figure out. Okay, so hopefully it wasn't as bad as you may seem then. Okay, now we go into our second derivatives. So we need a couple things before we do anything. And it doesn't matter which one you use, because again, they're the same. All right, so second derivative with respect to x is just going to be 12x squared. And this was also going to be 12y squared. And then our partial derivative portion. So let's see. I'll use this one. So now we take the derivative with respect to y only. So it'll just be -4. Okay. So now we want to find our d. So remember, we could plug in the point now itself for each individual point. Oh, actually, we'll do that later. We'll just plug these in. So it's going to be 12x squared times, so just in case you guys forgot what the equation is. Where's our equation? Oh, here it is. There we go. So this times this minus this, which is just -4 because, you know, the second partial was just itself. Okay. All right. Okay. Now that we have that, we got to check each individual point. So we're going to just do one, let's go down the list. So the first one, we'll use 0, 0. Okay, so first we got to find d. So plug in 0, 0 in for x and y. You guys agree all of that just goes away. And we get, this is going to be positive 16 minus, so it'll be -16. Well, -16 is less than 0. So according to our second derivative test, if it's less than 0, it's guaranteed to be a saddle point no matter what. So therefore, this is a saddle point. I don't even have to find f of xx. It's guaranteed. All right, number 2. We'll use 1, 1. So plug in 1, 1, so I get 12 times 12 is 124, 144 minus 16. What is that? 16, 120 something. But all I care about is it is greater than 0. So that works. So it does work. Next, we just got to figure out what is f of xx at the point. So plug in 1, that gives me 12. Right. So again, according to what we care about, b is positive, bigger than 0, so it's good. And we satisfy this. F, the second derivative, is greater than 0. So therefore, according to our definition, it is a local minimum. So this is a minimum value at the point 1, 1. And then finally do the last one. Okay. So it doesn't matter if it's 1 squared or negative 1 squared, it's still going to be 144 here. It's still going to be minus 16. So that's still greater than 0, which is all I care about. And then we do the same thing for fx. So if I plug in negative 1, I still get positive 12 out, which is greater than 0. So this also is a minimum. So we have 2 minimums and 1 saddle point. Interesting, huh? Now, if you're wondering, that does it really make sense? How can we have minimum and no maximum, right? Well, if you plug this into a GeoGebra or any software, we actually get this back. So this is the actual curve of our question. Now notice where our minimum values are, there and there, and our saddle point is there. So it literally looks like a saddle point, right? Like a saddle, if you guys do any horse riding or anything like that, hence the reason why it's called a saddle, right, in both directions. So notice there's no maximum, right? It doesn't go any dips itself. And we can transform this using level curves to see this. So now you can tell exactly where the points are, where the minimums are. And then the saddle point is exactly at the center, right? In this direction is getting higher, and in this direction is getting lower. So that's what the cool part about saddle points, and when you see above stuff and you go down on mountain ranges and stuff like that is, how does this stuff apply into actual space-wise? So all of this, level curve stuff can be applied into general formats. So now looking at this, you can tell where the minimum and max values are, or the saddle points are based off the level curves themselves, not just the actual portion. So this is the algebra to show the level curves. This is the geometric approach to show level curves and what the minimum maximum values are and the saddle points are of a function. So pretty interesting stuff, right? So crazy how everything actually, applies to itself. That's the things I like. All right, so before we finish up this section, let's do everybody's favorite. Some applications. All right. Applications of directional derivatives and all that fun stuff. So find the shortest distance from the point 1, 0, -2 to the plane x plus 2y plus z equals 4. So shortest means minimum, right? Here's our point B. So we got to find a Q, right? Call Q x, y, z, right? We have to find a point Q on this plane here. And I'm going to rewrite this to make it z equals instead. So just bring everything over to look like that. Okay. So distance. So the distance equation is this point minus that point. So it's going to be x minus 1 squared plus y minus 0 squared plus z plus 2 squared. Right, so we want to minimize that distance between that point and a point on the plane. Okay, so let's change this up a little bit to make this a little easier to look at. Now, unfortunately, when it comes to z is given to us to be this word. That's the reason why I made it solve for it. So instead of z here, I'm going to plug this whole thing in for z, all that bad boy right there. Okay. So when I do so, I end up being or getting the result of this, like that. Now I really hate square roots, right? So we're just going to tweak it a little bit. So we're going to square both sides. Make it somewhat easier and nicer to look at. Kind of, right? Still horrible, but still, square roots always make stuff horrible. Okay. So now we're going to find the partials. Okay. So let's take the partial derivative with respect to x. So that's just going to be 2 times x minus 1 to the first power times the derivative of the inside, which is just going to be 1. So just itself. That goes away, and plus 2 times all of this to the first power times the derivative of the inside is going to be -1. Okay, that wasn't too bad. Okay, do it again for now y. That goes away. This is just 2y and plus 2 times all of this times the derivative of the inside is going to be -2. Okay. So I'm just going to make this nicer to look at. I'm just going to rewrite a couple things. So if I distribute here and put everything together, so this gives you 2x, this gives you -2, and distribute all of this fun stuff, I get something that looks like this. And then do the same thing for y, distributing, and distributing this -4 to everything gives me this back. Okay. Now remember, to minimize something, we got to find the critical values. So we set each one equal to 0 and solve. So set it equal to zeros, meaning bringing this over and solve it for x and y. We get this. Okay. Now, this is where math gets more complicated, and you notice, questions get much more than just half a page long. All you have to do now is solve for a system of equations. You're like, oh, great, solve for a system of equations, really? Yes, you have to solve for a system of equations. So this one's not that bad, right? If I just multiply by -1 to, let's say, this one, and if I add these ones, the x's cancel. So you just get -14, or this gives you 10 is equal to -6. So you can solve for y and then just plug it back in. So we would get this back after we do that. And then once you solve for y, you plug it in any of the equations, solve for x, and that's how I got that number there. So again, right, multiply this by -1. So I could quickly do it here. That gives you 10. That goes away. This gives you 6. Divide it over, and that's how I got this. And then you plug it in back into here, and you get 11/6 there. All right. So that's our only point. So now we want to find the distance. So all we have to do now is, good thing we have calculators, is to plug it in into our distance formula. actually right here. Okay. Two times 5 is 10, so I'll just do that short. Okay. Now, after all of this multiplying, dividing, and all that horribleness, it's actually not as bad as you may think. This ends up giving 5 over 6. This is 5 over 3 still, and it's all things gives you 5 over 6, which is pretty nicely. And then squaring it, things cancel. I get this at the very end.